The useful question about artificial intelligence is changing. For years, the public argument has been about generation. Can a model write a paragraph? Can it produce code? Can it draft an image, summarize a paper, propose a molecule, or sketch a plan? Those questions still matter, but they are no longer the deepest constraint. The harder question is this: can the system prove that what it produced actually works? That question sounds smaller than generation. It is not. It is the question that turns a plausible output into something an institution can use. Generation and validation scale differently. Generation can be made cheap, parallel, persistent, and fast. Validation is slower. It requires tests. It requires data quality. It requires reproducibility. It requires provenance, audit trails, failure detection, and escalation rules for uncertainty. That is why validation is becoming operational infrastructure. Not a final checklist. Not a rubber stamp. Not the last box before deployment. Infrastructure. A candidate is something a system proposes. Evidence is what survives inspection. A candidate can be generated in seconds. Evidence has to be built, checked, reproduced, challenged, and sometimes rejected. The next phase of artificial intelligence will not be defined only by who can generate the most candidates. It will be defined by who can tell the difference between a promising candidate and a proven one. You can see the shift clearly in software. Modern coding agents can produce large amounts of code. Some can work for hours, use tools, run tests, inspect errors, and revise their own work. That is real progress. But code that looks right is not the same as code that behaves correctly under hidden conditions. A useful benchmark pattern now asks agents to reconstruct software behavior, not merely write plausible code. The agent can observe a program, run examples, inspect visible tests, and then face hidden tests it has not seen. The important part is not just whether the agent writes something. The important part is whether the work survives independent validation. That exposes the gap between output and proof. A system may pass most tests and still fail the case that matters. It may satisfy visible checks while missing an edge condition. It may produce a patch that looks reasonable, compiles cleanly, and even passes the available test suite while still being wrong in a way the test suite never covered. That does not make the benchmark useless. It makes the benchmark more honest. It tells us that evaluation is not a neutral window onto capability. Evaluation is part of the system. If the tests are weak, the apparent capability is inflated. If the tests are visible, agents can optimize around them. If the hidden cases are too narrow, the benchmark measures a smaller world than deployment. If the data is messy, duplicated, contaminated, or poorly labeled, the evaluation inherits those weaknesses. This is why validation can no longer be treated as passive measurement. A validation layer has to be designed. It needs executable specifications, a way to turn intent into something that can be run, measured, and falsified. Natural language goals are useful, but they are not enough. A team needs to know what success means in operational terms. It needs private tests and adversarial edge case discovery. Visible tests help systems make progress. Private tests help prevent shallow success. Edge cases reveal where a system is matching the easy shape of the task without understanding the hard boundary. It needs provenance. Someone should be able to reconstruct what the system saw, what it changed, what it tested, what failed, what was ignored, and why the final answer was chosen. Without provenance, success becomes a story. With provenance, success can become evidence. It needs reproducibility. If a result depends on a fragile environment, a hidden dependency, a lucky random seed, or an undocumented manual step, then the output is not yet institutional knowledge. It is a performance that may not repeat, and if it cannot repeat, it cannot become a dependable process, no matter how impressive the first demonstration looked. It needs escalation. A serious system must know when not to proceed. Confidence without an escalation path is not reliability. It is a failure mode wearing the language of certainty. This is especially important because benchmark success is easy to overread. A benchmark can show that an agent performed well under defined conditions. It cannot, by itself, prove production readiness. Production adds security, maintainability, integration, changing requirements, user behavior, economic incentives, and failure consequences. A hidden test suite can be strong and still not represent the whole operating world. That is not a criticism of benchmarks, it is a boundary around what they can prove. The same boundary appears in scientific and technical work. Artificial intelligence systems can propose hypotheses, write analysis code, search design spaces, and produce experimental candidates. That can accelerate the front end of discovery. But discovery does not end when a candidate appears. In many fields, that is where the expensive part begins. A candidate molecule still has to be synthesized or tested. A proposed material still has to survive measurement. A simulation result has to be reproduced. A method has to be documented well enough that another team can follow it. A medical or industrial claim has to pass domain-specific evidence standards. The limiting layer moves from imagination to proof. And proof is not generic. Software validation is not the same as biomedical validation. Material science is not the same as finance. Infrastructure systems are not consumer apps. Each domain has its own definition of acceptable evidence, acceptable uncertainty, and acceptable risk. That is why the phrase artificial intelligence will validate everything is the wrong frame. Validation is not one universal function that can be poured over every generated output. It is a layered, domain-specific practice. It includes tests, audits, replication, data governance, review processes, institutional accountability, and judgment about what happens when the evidence is incomplete. The more capable the generator becomes, the more pressure moves onto that layer. What we can call validation debt is the backlog of plausible outputs whose evidence chains have not yet been evaluated. Every generated patch, plan, analysis, experiment, image, or recommendation creates a proof obligation. If an organization can generate 100 candidates in the time it used to generate 10, it has not automatically become 10 times more productive. It may simply have created 10 times more work for the people and systems responsible for deciding what is real. That is the operational trap. The output pile gets larger. The evidence layer does not scale at the same speed. Review queues grow. Test suites become the throughput limit. Domain experts are asked to inspect more artifacts. Teams begin to rely on proxies because full validation is too expensive. Eventually, the organization starts mistaking plausibility for readiness. This creates a different capacity question. It is not just, how many candidates can the system produce? It is, how many candidates can the organization responsibly clear? How quickly can it find the bad ones? How much evidence can it preserve without slowing everything to a halt? How many failures can it learn from before those failures reach users, patients, customers, markets, or infrastructure? That is validation throughput. Validation throughput is not the same as review headcount. Adding more reviewers may help, but only up to a point. The deeper issue is whether the work arrives in a form that can be checked. A well-instrumented system produces artifacts with tests, logs, assumptions, data lineage, and known failure modes. A poorly instrumented system produces impressive-looking answers and leaves the institution to reconstruct the evidence afterward. The first system compounds learning. The second system compounds uncertainty. This also changes procurement and deployment. A model demonstration can show possibility, but a validation system shows readiness. Before an institution relies on an output, it needs to know which data was trusted, which tests were independent, which assumptions were contested, and which failures would stop the process. Without that, deployment decisions become a bet on surface fluency. With it, deployment can become a managed risk decision. This is also why auditability matters before a crisis, not after one. If the evidence path is captured only when something goes wrong, it is already too late. The useful record has to be built while the work is happening. What inputs were used, which alternatives were rejected, which tests failed, which warnings were overridden, and which human decisions changed the path. In that sense, validation is not only a technical layer, it is an organizational memory system. It tells the next team what was tried, what held up, what broke, and what should not be trusted yet. This is where trust enters the story. Institutional trust is not built by confident output. It is built by repeatable proof. People trust systems when they can see how conclusions were reached, when failures are visible, when uncertainty is handled honestly, and when there are consequences for being wrong. A system that cannot explain its evidence path may still be useful for exploration, but it is harder to make operational, it is harder to audit, it is harder to regulate. It is harder to defend after failure. That means validation capacity becomes a strategic asset. Models matter. Compute matters. Data matters. But the organizations that benefit most from increasingly capable artificial intelligence may be the ones that can build the strongest proof layer around it. They will be able to translate messy goals into checkable work. They will maintain private tests that adapt as models improve. They will track provenance by default. They will detect silent failures earlier. They will separate generated from verified in their workflows, and they will know when a result is ready for deployment, when it needs more review, and when it should be rejected. This is a quieter kind of infrastructure than the model itself. It does not look as dramatic in a demo. It does not produce the viral screenshot. It does not promise instant transformation. But it may decide what can actually be used. There is an important counterweight. Validation is not the only constraint. Some domains will be limited first by data access, physical experimentation, integration cost, regulation, security, compute, or organizational incentives. In some settings, the proof layer is only one constraint among many. But wherever artificial intelligence systems can generate work faster than institutions can inspect it, validation becomes the limiting layer. That is the shift. The frontier is not only whether an artificial intelligence system can produce an answer. The frontier is whether the surrounding institution can prove which answers deserve to move forward. That is the shift. The frontier is not only whether an artificial intelligence system can produce an answer. The frontier is whether the surrounding institution can prove which answers deserve to move forward. If this episode helped clarify the validation bottleneck, subscribe to Quantum Convergence AI for more work on the infrastructure behind useful intelligence.